For our next guest speaker, Alasdair Collinson. Big round of applause, guys. Give him some energy. His slide says it all. The quantum computers are coming. It looks scary, but interesting. Floor is yours.
Thank you very much. Is this on? Can you hear me? Ah, that's better. Wonderful. Yeah, it looks scary. Turns out it isn't as scary as it looks at first. But we'll come to that soon enough. So, my name is Alasdair Collinson. I'm a software developer for Xenocor Technologies, and blah, blah, blah. You don't care about any of this, do you? The fact is, there's one thing you have to know about me, and that's I'm a nerd. In fact, I'm such a nerd that my colleagues call me a nerd, and they're, computer scientists and mathematicians and physicists. Now, personally, I'm not a physicist. I've learned a bit of physics, but I wouldn't call myself a physicist, certainly not a classically trained one. And yet I'm here to talk about quantum computers. And I mean, that quantum part there does sound rather physicsy, doesn't it? Thing is, quantum computers are coming to a stage where you don't have to be a physicist. Being a nerd is quite sufficient. And that's a good thing, because looking at you, it's the second day of the conference, Saturday afternoon, the second to last talk, and you're sitting here for a talk on quantum computing. I think chances are you too are nerds. So, good things, good things. Okay, so let's start. Quantum computers, let's start with the easy part. What's a computer? Well, this is a computer. Slightly older and more clunky than what you're probably used to, but it is a computer. This is, in fact, a copy of the Zuse Z3. When people argue about what the first computer ever was, this is certainly a candidate. It was the first electronic, digital, and binary computer. That last part, binary, that's important because chances are that every computer you've ever programmed on is binary. Not all computers in history were binary, but it's kind of the default now. And when we think binary, we normally think of ones and zeros, but it doesn't have to be ones and zeros, really. I mean, we need two things that we can keep apart, two distinct values. For all we care, that could be a green circle and a red triangle. And what computers do nowadays is they work with transistors. Well, not with these. They look rather like this. There are loads and loads of transistors in there. The way a transistor works is that it has two inputs, one output, and if the combined input is large enough, it will give an output, otherwise it won't. Two distinct values, electricity or no electricity. And this is really great for many, many problems. And just look at what we've been able to accomplish with computers, with classical computers in the last few decades. It's astonishing. But there are tasks that classical computers are not that well suited to. So, looking at, as I found out earlier, a bunch of nerds, this might be shocking or even new to you, but I'm going to talk about nature. So nature is not easily separated into distinct categories. And look at this picture, and we'll try to find out where there's forest in this picture. Zoom in a bit. And so this part, that's certainly a forest, right? We can agree on that. And that part there, that's probably not a forest. But what about this area? There are trees there, but most of it is grassland. So we have to decide, okay, how do we differentiate between forest and not forest? And I mean, you can do things like say, okay, if you have so many trees per square kilometer, it's a forest, and if it's fewer, then it's not a forest. We're drawing an arbitrary line there. We have to decide what the distinction is. And when you have to decide where the distinction is, you lose information. In many cases, this doesn't matter at all, but there are cases where it does matter. So that's the computer part of quantum computing. Let's get to the quantum part. And don't worry, this won't be a deep dive or anything. It's just a very, very quick overview over what you have to know for quantum computing. So quantum computing started with two guys, Niels Bohr and Werner Karl Heisenberg. And those two worked together in the 1920s in Copenhagen. And they came up with quantum physics, quantum mechanics, and what came to be known as the Copenhagen interpretation of quantum mechanics. And I'll explain the Copenhagen interpretation with a rather simple example. So let's take an atom. In fact, we don't care about the whole atom. Let's take just the nucleus. Now, if this material, this atom, is radioactive, that means that at some point, part of the nucleus will split off. That's the radiation we get. So, assuming we have our atom, our nucleus that is radioactive, and we wait for a while, there are two states that we could measure it to be in. Either, well, nothing changed, or it has decayed, and what remains is a different element plus the radiation. According to the Copenhagen interpretation of quantum mechanics, you can have both of these states at the same time. That is, until it is measured. At that point, one or the other state becomes the dominating one, the real one in quotation marks. Now, don't be confused by those eyes. Measurement does not have to mean that someone is looking at it. We are not connecting consciousness and physics here. Measurement can just be that something requires that this has a definite state. And humans looking at it is just one way to measure. But it's still a very, very weird concept. And we're not the first to think that it's weird. So this here is Erwin Schrödinger. And he thought that this was pretty weird. He was a physicist, and he came up with a thought experiment which explains how weird the Copenhagen interpretation is. And for this thought experiment, we need his famous cat, Schrödinger's cat. And what do we do? So the experiment is rather simple to explain, not quite as simple to understand. But basically, so first of all, we put Schrödinger's cat in a box. And there's more than just the cat in the box. So what else do we have here? First of all, we have a radioactive source. Now, this is basically what we saw with the radioactive atom, the nucleus, earlier. But this source is chosen very specifically so that after 1 hour has passed, the chance that we would measure any radiation whatsoever is 50%. Okay? So, radioactive source, cat. What else? Well, there's a bottle of gaseous cyanide. If that gas should leave the bottle, well, that won't be good for the cat. But currently, it's safely in the bottle. Everything's good. Schrödinger is devious, however, and he also puts this weird contraption in the box. So this is a Geiger counter, which measures radiation, which has a hammer attached to it. And if the Geiger counter registers any radiation whatsoever, this happens. Dead cat. So let's remember what we learned about the Copenhagen interpretation. After 1 hour, we would normally expect to measure either the case where nothing happened, the radioactive source is intact, the cat's alive, everything's wonderful, or, not so much. But according to the Copenhagen interpretation, you can have both of them, both of these states at the same time, overlapping. That would make the cat dead and alive at the same time. I mean, what's dead and alive at the same time? I don't think he was thinking zombie cat, actually. So Schrödinger did believe that quantum mechanics in theory was correct. He just thought that the interpretation was nonsense. He came up with his own interpretation, and that became known as the many worlds theory. So the many worlds theory will be useful to us in this quest to understand quantum computing. I do have a disclaimer. The many worlds interpretation or many worlds theory for us is a model. And like all scientific models, it can be wrong in many, many ways. But it can be right in other ways. And as long as the ways it's wrong is ones we don't care about, so what? And luckily, this is a case where even if the many worlds theory should turn out to be wrong, it's useful to us for this purpose. So, many worlds theory, how does it work? Let's imagine the universe. Of course, this is a galaxy. I couldn't find a picture of the universe, but just take it as the universe. And among other things, in this universe, we have our cat, or Schrödinger's cat. So, what happens? We have our quantum event, the possible but not certain measurement of radioactive decay. And what happens then is not that you get your zombie cat, but rather, and this is one reason I really love physicists, the universe just carbon copies with one difference, and that's the effect of that radioactive event. So in one universe, the cat is alive, in the other, it's dead. Otherwise, they're exactly the same. And if another event happens, the whole thing copies again. And so on. You get the understanding. Now, if you ignore the implications of this, most of the implications, this is really the theory. It helps us think about these multiple states in interesting ways. There's something else you might see here, and that's we have rather many dead cats there. And in theory, there we go, dead cats. Why is that? Well, thing is, biology is in our way. If you have a dead cat and add more poison, you don't get a live cat. But luckily, qubits, which is what we care about for quantum computing, are not like cats. They can be reversed. So, qubits. Let's have a look at qubits. This here is what's called a Bloch sphere. It's a kind of representation of qubits, or quantum bits. And I find this to be very, very useful. How do you read it? What can you do with a qubit? Well, you can manipulate stuff in it, and you can read it. When you read it, it will have a definite value. So it can have this kind of value, in which case, if you read it, you'll get 0. It can have this kind of value. If you read that, if you measure it, it will be 1. You can also have this kind of value. And this is the case where you could get 0 or 1. And actually, this is a combination of the 0 and the 1 factor. Now, this looks a bit weird. How can a sum of something that's up there and something that's down there be somewhere over there? Don't let the math confuse you. We're not going to need any of it, and it's complex. It makes sense, but we don't have to care about it. So, okay, I said we can do operations on our qubits, and these operations are in the form of gates, quantum gates. First one I want to talk about is the so-called Hadamard gate. The Hadamard gate takes a qubit, and it imagines an axis halfway between the x and the z axis. And then it spins our vector around that axis. So if you were to measure this qubit now, you would get either 1 or 0 with 50% probability each. So this is basically the state our cat is in. It could be dead or alive. It's kind of both, but at the time that we check it, it becomes one or the other, because this can only give us as an output 0 or 1. It can't give us anything else. So you have to, well, it has to decide, in quotation marks. There's no real decision. It's just probability. So this is what's called quantum superposition. There are several different states superimposed over each other. A rather simpler gate is the Pauli X gate. So if you have your qubit in state 0 here, and you apply an X gate, it will just take the X axis, that's where the name comes from, and spin our vector around the x-axis by 180 degrees. So we know this kind of behavior from classical computing. This is basically a knot. It's a knot around the x-axis, and there are equivalent knots around the y and the z-axis, but this doesn't seem too unfamiliar. So that's good. Something familiar is good. There's an enhanced version of this as well, and that's the conditional knot, the C knot. And now we have a 2-qubit gate. So first of all, we have our measurement gate. That's this one here that's wobbling. And this gate, or control gate, is checked in a way, and the gate can then have an effect on the other gate. So if we apply our C0 gate, in this case, nothing will happen. Go back there. I'll go back, exactly. Because 0 in the control gate means do nothing. The condition is not met, so everything's wonderful. If, however, we start out with the control gate at 1 and apply our Hadamard gate, our other gate, our target gate, will be changed. An X gate will be applied to it, basically. So that's fine. We could basically program this kind of stuff with an if-then-else statement, right? What about this case? Our control gate is now in superposition. And then we apply our C0. We get something a bit like this. 2 arrows. They are now superimposed as well. It's basically like you have this kind of stuff. So in the case that our control qubit would be measured as 0, nothing happens with the target qubit. In the case that it would be measured as 1, the target qubit is flipped. But this is basically what we had with the radioactive isotope and Schrödinger's cat. Either both things happened or neither happened. You don't get cases where 1 is 0 and 1 is 1, if this is your basis. This is what's called quantum entanglement. So 2 qubits are connected in a way that they will both read out, well, not necessarily the same, because if we had started with the second gate as 1, it would be opposite. But they are dependent on each other. And as long as we don't measure, we still have an overlap. So this is not, when we use the C0, we are not measuring the gate. We are not forcing it into one position. We are leaving it in superposition and moving the superposition to also encompass the other gate, the other qubit, I mean. And this allows us to do really interesting things with quantum computers. So, okay, I've talked about the Hadamard gate and the C0 gate. I showed you one of the three Pauli gates, the X gate. As I said, there are others for Y and Z as well. I didn't show you the identity gate because that's boring. It just takes a gate and leaves it as it is, identity. There are other gates as well. For example, there are phase gates. Not going to go into those. They let us do different rotations within the Bloch sphere. And there are many, many more you can think of. So, okay, that's the theory. Now, what are the use cases? Why should humanity care about this stuff? Well, there are many things you can actually do with this kind of thing. And often when you read about quantum computers in any popular science outlet, what you'll hear is quantum computers will break encryption. So there are a few algorithms that have been designed specifically for quantum computers. One of them is Shor's algorithm. And Shor's algorithm is really, really good at factorizing numbers. Now, many modern encryption algorithms are based on the idea that if you multiply two huge prime numbers, factorizing their result will be really, really expensive. But Shor's algorithm is much more effective at that than any classical algorithm could be. So that's potentially a problem. But there are other things you can do with quantum computers. Volkswagen is using quantum computers in cooperation with Google to research engineering questions. And there's stuff about simulating chemical processes with quantum computers. Because, of course, chemistry is quantum in nature. And if you have something that is more similar to the nature of the problem, it's easier to simulate that. More close to what we do, you can use quantum computers, potentially at least, for AI applications. You can use quantum computers to improve weather prediction, potentially. Or how about detecting financial fraud? NASA is in the quantum computing business, researching engineering questions similar to how Volkswagen and Google are doing it. And just as a warning, and this is connected to the first example I gave, quantum computers can break Bitcoin. Because cryptocurrencies, the crypto prime factors, problem. So, I mean, we're not there yet. If you have Bitcoin, you're probably, well, as safe as you can be with Bitcoin for the moment, but perhaps not wait until quantum computers are strong enough, fast enough to crack Bitcoin, because then you're in big trouble, probably. Well, out of money. Okay, that's what could be done with quantum computers. Why should you care? Well, you can get into quantum computers now, and there are a few good reasons to do so. First of all, never a bad thing, job security. Quantum computers are coming. Companies are starting to look for people with knowledge of quantum computers. Actually, yesterday, the first, to my knowledge, ever job fair for quantum computers and quantum computer scientists mainly was held in Bristol in the UK. Things are moving quite rapidly. Companies are looking for people with expertise in this field. And most people with expertise in the quantum computing field come from a physics background, or at least a scientific background. We here, many of us work in industry, and we are challenged by different kinds of problems, in many cases, than scientists are in their labs. So to steer quantum computing in a direction that's relevant and interesting to us, we have to be active. There's another point that I would like to make, and that's actually a quote from Venkat, who spoke yesterday, gave the closing keynote. He tweeted out this in January. Basically, if you learn something new, choose something that's different from what you know because it widens your horizon. And Venkat is, of course, not the first person to say something of the kind, not the only one to say that stuff. In fact, the closing keynote today will be about being polytechnical, learning loads and loads of different things, at least a bit of them, so that you can apply knowledge from one section in a different area. This is really interesting, and I'm looking forward to the keynote. So, though, as far as I know, he's not going to mention quantum computers, it's valid as an argument here. Okay, so that's the why. Now, how? How can you get active in the area of quantum computing? I mean, you can't just go and buy a quantum computer, set it up at home, and start working with it. Not yet, at least. But there are things you can do. So the first project I want to introduce to you is the IBM Quantum Experience. The IBM Quantum Experience is basically quantum computers in the cloud. IBM built several quantum computers, and the quantum computer in this picture is actually inside this. This isn't the quantum computer itself. This is a cryostat, a huge freezer. The quantum computer itself looks like this. This is specifically a 7-qubit quantum computer, 7 qubits. And most quantum computers that are around, at least to the public, available to the public today, are based on can't remember the word. Superconducting, that's the word. Superconducting technology, which has to be cooled down as far as possible. And I mean, these things are cooled down to temperatures colder than you would find in outer space. Millikelvins above absolute zero. Well, that's redundant, but millikelvins. Really, really cold. That's not really practical for our kinds of uses, but IBM makes this available via the internet. So what we see here is the login page for the IBM Quantum Experience. You can register there for free and use the service for free. And they have lots of great learning material. The thing that I'm going to talk about mostly today and where you will probably spend most of your time is this page here. So this page has, it's 3 sections. I'm ignoring the bottom one because that's just results of experiments you've done. The top section here shows you the status of the quantum computers that you can access. So here we have 2 quantum computers. One of them at the time I made this screenshot was in maintenance. The other one was active. It gives you loads and loads of information, including the temperature. Okay, normally it does. In this case, empty list. Well, software. And this can be useful. We're not going to go into that particularly. What's much more important for most cases is this. This is the quantum composer. Named so because, it looks a bit like a musical score. And the quantum composer is where you'll write quantum algorithms, in many cases at least, if you use the IBM Quantum Experience. So to the side here, we have the gates. Those include the gates I showed you earlier, the X gates, the H gate, that's the Hadamard gate, and that circle with a plus in, that's the C0, and a number of other gates as well. So, okay, we have 5 qubits here, 5 lines, each one representing a qubit. We have our gates. Let's build something. And we've seen one example for an algorithm already, a very simple one, but let's build Schrödinger's cat in the IBM Quantum Experience. So what do we need? We have the cat, of course. We have the radioactive source. We have the Geiger counter with a hammer. We have the poison. And we know that all of those are connected. And they're connected in sequence, right? So let's move that into our quantum composer. There we go. Easy enough. OK, I don't have a radioactive symbol or a cat symbol in the quantum composer. There are gates there. So basically, the radioactive symbol, that's putting something into superposition. Or, well, it is in superposition. That's the Hadamard gate. And then, basically, we just connect all of the other gates via C-knots. Because if nothing has happened with the radioactive source, then nothing should happen to the Geiger counter, nothing should happen to the poison, nothing should happen to the cat. If the radioactive source has decayed, everything should happen. And we measure this. We look into the box with this pink gate here, the measurement gate. In fact, let's add more measurement gates. Let's have a look at all of those qubits that we're modifying. And you can run this. Now, IBM lets you run this in two different ways. You can run it on a simulator, or you can run it on a real-life quantum computer. And they have a system to protect themselves a bit, but basically you can use this for free. You may have to wait for a bit. Okay, so the results, if you run this on the real quantum computer, may look something like this here. Yeah, what does that mean? Okay, so we have a peak here. At the bottom you see only zeros. That means nothing happened. 0 is the standard state of the qubits. Then over here we have a peak. And we'll ignore the first 0 because that's the qubit we weren't using. Everything else is 1s. And that's good. That's expected. If the radioactive isotope did decay, blah, 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 the cat's dead. But we do have this. Now, the numbers above, those are percentages. And we ran, I think I ran the experiment something like 1,000 times. And in approximately 30%, we get each of the expected results. But that still leaves 40% that it's somewhere there. Yeah. Oops. Thing is, quantum computers are still relatively early in error correction. Quantum error correction is a huge issue, and people are working on it. But you do see a lot of errors. So you currently have to know what to expect and thereby interpret your results. That's not a perfect world. I'm sure it will change in due course, but that's the state we're in right now. Okay, next project, the Microsoft Quantum Development Kit. Now, this is much closer to what we know as code from our everyday lives. You can, by the way, with the IBM Quantum Experience, also use a language called QASM, Quantum Assembly, and there's a Python library to go with it, and you can interface with that. Not getting into that because we have a similar example from a different project coming up. But okay, so the Microsoft Quantum Development Kit, that comes with a language called Q#. The name implies that this is somehow connected to the .NET landscape, and that is in fact the case. But okay, so a Q# program. I've blurred out what we don't need for the moment, so it's not your eyes. What do we have here? First of all, we use a Hadamard gate on what we represent as our isotope. And then we apply a C0 to it and the Geiger counter, a C0 to the Geiger counter and the poison, a C0 to the poison and the cat. You know this by now. So that's basically our quantum algorithm there. Then we have down here, up there we set up a mutable value which represents whether the cat is alive or dead. Then we look into the box and interpret the result and return, did the cat survive? And then there's some boilerplate code here. We have to decide, okay, we're using 4 qubits, and there you get an array of qubits, which is okay, but maybe use informative names. So we'll give them names. And we do have to initialize them to 0 in in Q#. Okay, let's do that. And we have to clean up after ourselves as well, so set them back to 0. Okay, that's limitations the language gives us. There are good reasons for those limitations, which, again, I'm not going to get into. So this is our Q# code. And then we have a program in a .NET language. This is C#, where we can call our quantum code, and we give it, in this case, a quantum simulator. Now, the quantum development kit does come with a quantum simulator. It does support other implementations, and I know that people are certainly working on implementing this for the IBM Quantum Experience, so you can use those at least as soon as that works in tandem. I don't know what the status of that project is, but I know it exists. And then, run the experiment with that simulator and give us output. So this is rather simple, and we can use it in combination with languages that are more familiar to us. And this is something that will happen. We will use, when quantum computers become more powerful, quantum computers in combination with classical computers. There are things that you really don't want to do with a quantum computer. You don't want to build, for example, an adder with a quantum computer. An adder would be basically a C0 if you just choose one bit and accept overflow. And that will give you 0 if both are 0, and 1 if either is 1, and 0 if both are 1. So that works, except there's that error rate. You don't want to have, okay, I think 1 plus 1 is 2 with 40% chance and probability. Yeah, don't do it. Use regular classical computing gates, regular classical languages for that kind of problem. Okay, another example where we use a classical and a quantum language in combination is Rigetti Forest. Now, this is a relatively new project. Rigetti is a quantum startup, because of course there are quantum computing startups. And they describe themselves, or they describe Forest as an API for quantum computing in the cloud. So this is a very, very similar concept to what we saw with the IBM Quantum Experience. And they offer a few things. One thing they offer is a quantum computing or quantum programming language they call Quill. So in Quill, this is our algorithm. And this is really straightforward. You have your Hadamard gate, your C0s, 1, 2, 3, and then you measure the whole thing. Really, really simple. And you can either write a Python program which reads this in and then sends it to the API, or you can program it directly in Python. And this is our quantum algorithm. It looks basically identical to the Quill program. So you can send this to a real quantum computer or a simulator. Now, we've been talking about, or I've been talking about simulators. So if we can build quantum computing simulators, why do we need real quantum computers? Why do people care about building these highly complex machines if you can simulate everything? Well, remember this slide? In theory, when I press my clicker, there should be a smooth transition where the dead cats are replaced with gravestones. So I've pressed the button. There we go. That was not smooth. My computer is struggling with PowerPoint. Now, this here, come on. There we go. This here is Google's Bristlecone quantum computer, the largest in number of qubits quantum computer currently known, at least to the public. whether the NSA, for example, has something larger, and I'm sure they're into quantum computing, as I said, breaking encryptions and so on. This is the largest one known to public, and it has 72 qubits. And this was introduced in March. And about 3 weeks ago, Alibaba, the Chinese internet company, published a paper where they basically said, hey, we've improved quantum simulation. The Google chip would be somewhere around here. And we did this using about 130,000 processors and 1 petabyte of memory. This is a huge improvement, but still, 131,072 CPUs. So let's think about that. The processors they used, as far as I can determine, have about that size. It turns out that that would give you about 565 square meters. So, yeah, anyone recognize this part of the Acropolis? The main temple up there? Well, if you do the calculations, it turns out spreading out all of these processors on the ground would fill it to about a quarter. That's a lot of space for processors. And when it comes to memory, well, they said 1 petabyte, that's 1,000 terabytes, that's 1,000,000 gigabytes, that's 10 to the 15 bytes. 10 to the 15 bytes. So one person, according to a study I found, has about 3.72 to 10 to the 13 cells. So that would be not one person, not 2 people. That would be the cells in 27 people, approximately. Voxxed Athens has about 30 speakers. So if you would line all of us up and count the cells, you'd be very close to the amount of bytes you'd need for this simulation. So that's a lot. They used a supercomputing cluster for that. OK, so let's just rehash what can you do if you want to get into quantum computers. Well, the IBM Quantum Experience, you can sign up for free. Here's the URL. I'll put these slides online, so you don't necessarily have to write all this down now. The Microsoft Quantum Development Kit, available for Windows, Mac, and Linux. Also available for download. Forest, you can register for free and use that. There's good documentation on that. There's also a quantum stack exchange, so Stack Overflow for quantum computing. You can register there for free. It's in public beta at the moment, I believe. You can find that here. And if that's all too heavy for you, you want to start with something fun, well, there's this game, Hello Quantum, written in Python and in cooperation with IBM. Basically, it looks like this. You have to apply gates and so on, and you can find it. Well, it's a weird URL. I just created a tiny URL because nobody would be able to remember that. And if this is too, primitive an interface for you, and you have an iOS device, well, there's also a version for iOS that you can download on the App Store and play. And this is a great little game, lot of fun, and it teaches you about quantum computing. And with that, I'd say, if the slide will change, there we go. Try it out, play around with quantum computing, and join the revolution. Thank you very much.
And we have time for 3 questions before we join everybody for the closing keynote next door. So, questions? It was all very clear.
OK, if nobody can come up with a question. Oh, there's a question. Was that a question? No, okay. If nobody has a question right now, I'll give you some time and tell you something that I'm asked ever so often, and that's about quantum supremacy. So when you look into quantum computing, one thing you'll stumble over relatively quickly is quantum supremacy, and that's basically, well, it's a weird concept. The idea is quantum supremacy is the point at which we have a quantum computer which could do things that a classical computer can't. These things don't have to make sense. But as soon as you can write something that a quantum computer can do and a classical can't, at least not in realistic time, quantum supremacy will be reached. Now, Bristlecone was a candidate, many thought, for quantum supremacy being reached. It has 72 qubits, as I said, and the previously largest one I'm aware of had 50 qubits. The largest simulation there was until the paper from Alibaba came out was, I think, 56 qubits being simulated in realistic time. So the bar has been moved. I think with that paper it's up to something like 124 qubits that can be simulated. But the meaning of quantum supremacy is not as big as you may think. I mean, the term sounds great, it sounds grandiose, but I mean, if you can simulate something doing nonsense, or you can't simulate something doing nonsense, what's the difference? As soon as you get to quantum computers that can do something really useful, that'll matter. But probably you'll need something in the at least hundreds, probably more likely thousands of qubits working in parallel with much lower error rates than we get right now. These things are going to happen. I would estimate that within the next 5 years or so, we will have cases relatively commonly where businesses do use quantum computers, or at least start using quantum computers for, at first, very limited purposes. And I mean, one reason that these are limited one reason is that you can't really have your own quantum computer at a large scale if you need this huge cryostat and have to cool it down to close to absolute zero. There are technologies for quantum computers that don't need this, but they're not as advanced at this point. Currently, the version of qubits that has to be cooled down to near absolute zero is the best kind we have. Okay, that's me telling you a bit more. Any questions now? Okay.
Any questions to that? No?
Okay. Then
okay.
Thanks
so
for
thank
listening.
you. Thank you.
All cats are safe.